Good evening, everyone. Wish you all a happy Vasant Panchami. So we are uh, continuing this introduction or detailed introduction to this course on DC machines primarily, but during uh, during the introduction, I am taking this opportunity to introduce to you the different machines from field perspective, so that we can have a clear understanding of these all machines. Basically, I wanted to um, give the field level understanding of all machines, so that we understand all machines and working principles of all the machines from field electromagnetic field point of view. So we have discussed the magnetic field due to coils, then realization of stator of DC machine, that is nothing but an iron core coil. We looked at the field of the DC machine, and then we looked at the principle of torque production. Basically, we need two magnetic fields, and there has to be two some phase shift between the two. And in order to have some the continuous torque, we need to have two magnetic fields which are stationary with respect to each other. So then we went on to see that we can have the stator magnetic field either stationary or rotating. So we have that is where we started last day's session. So we understood that if we have we have a stator like this, and if we excite some DC current, and we look at the air gap flux density distribution, that is, we move around on this red circle, and on all points we note down what is the flux density. And flux density obviously has some magnitude as well as direction. So I'd like to request all of you to mute yourself. So we assign whatever radially outward sign. If flux density flux direction is radially outward, we assign positive sign to it. That is where it is positive here, around 90 degree. And if it is radially inward, that is like this case under the north pole, we assign negative sign to it. So this is how we get the B distribution, and because the current is stationary, so the B field in space also does not change, it remains the same if only this stator coil, some DC current is passed through this stator coil. Now we try to realize or try to understand what happens if we inject some sinusoidal current. So the same structure, we inject some sinusoidal current, and we looked at the animation that shows that flux, basically the field, sometimes it is zero, sometimes then it increases, then it reverses, flips its sign, and like that it goes on. So we have a pulsating or an alternating magnetic field. Then we went on to see point by time instant by time instant what happens. So this is another animation which shows that the flux density distribution here in air gap, that is basically pulsating with time. Then we understood about three phase and multi phase. So the basic understand so because we have three phases, so we can distribute the three phase axis symmetrically with respect to each other, and we can make winding accordingly. And we have seen that for multi phase we have to distribute uh, the axis like this, where m is the number of phases. And we also understood that m has to be greater than equal to 3. For two phase machine we have to distribute the winding like this, so they have to be perpendicular, or basically 90 degree shifted from each other, and the currents that we have to inject, they also should be 90 degree phase shifted with respect to each other to have the same effect, that is the rotating magnetic field. We looked at that. So this is the construction: R phase, Y phase, B phase, and the concentrated coils wound around each pole, so that we have R phase axis vertically, Y phase axis at 120 degree, and then 120 degree to the R phase axis, and again B phase axis 120 degree away from the Y phase axis. So if we inject three phase sinusoidal currents to this winding, then we saw the animation that we will have a revolving magnetic field, the magnetic field which is rotating at the speed corresponding to the electrical frequency. So because we have given 50 hertz of excitation, so what does 50 hertz mean? 50 hertz means the 50 cycles. So 50 cycles
got unmute, sir.
I have to simply, I'm unmuted only, so I
No,
have
it's
to,
okay.
yeah, so I have to,
Audible.
okay, so I have to multiply it by 60. I have to multiply it by 60 in order that will give me 3000 rpm. So we see, if we look at, actually it is the field, rotating field, that is actually rotating at 3000 rpm for this type of excitation. And from this you can clearly see that if we vary the excitation frequency, then it is possible for us to vary the rotating speed as well. So this is where we kind of stopped. And okay, we also looked at the different cases. So we are looking at the time instant, that is theta equal omega t equal to 0, that is the time angle. And at that instant, if we traverse on this black circle, then what is the field distribution. So we looked at that. And if we move ahead in time, then we see that that basically shifts in the right hand side direction, or it basically moves ahead in space also. And we can look at that in a detailed manner, or basically we can have the animation to visualize it better. So you can see that on the left hand side, as the time instant keep on progressing, the field also progresses in space. So this is about the basic understanding about how does rotating field, how can we have rotating field generation. But if I so this is the construction that we have for three phases. Now for this case, you can understand that in this case the coils are basically wound around each pole. So if this is one pole, then the coils are basically wound around like this, wound around the pole like this, right? This is how the coils are wound. And this type of winding is named as concentrated winding, because it is concentrated around the individual poles. Now you will see that mostly in AC machines, mostly in stator or AC machine winding, whenever it is introduced to you, we are told that there is a distributed winding. So this initial portion was just to tell you that, yeah, if we follow the principle, it is actually possible to do it with concentrated binding also. And actually for if the number of poles is actually very high, say beyond 4 8, it goes to 32 64. If we actually want 36, that many number of poles for some special kind of applications, then we actually go for concentrated winding kind of construction. But for mostly 2 pole, 4 pole, 8 pole, this type of cases, we mostly go for distributed winding. So let us try to understand distributed winding, because that is most common. So first let us try to see, is it possible for us to realize this r phase axis in some other way. So we are keeping the geometry same, the geometry of the stator remains the same. I am just asking, is it possible to realize the r phase axis in some other way. We will put the r phase axis, r phase coils in some other locations, and still realize the same r phase axis. So actually I'll just tell you that yeah, it is possible. Say I place my two coils here in diametrically two opposite slots. So I fill the entire slot with R phase coils, and I put a dot here, and I put across here, right? If my coil is like this, so just to give you a visualization, if this is the cylindrical stator or rotor, whatever you can think it as. So the coils are basically going like this. The coils are basically going like this. They are completing their path like this, and they are going back to the diametrically opposite slot, and they are coming out from that. So this is one coil. I hope it is understood from you. So this is the stator, or whatever, this is the magnetic part, cylindrical. And I'm putting, so there are many slots on that. and through one slot I am putting one side of the coil. It is going all along in the axial direction, and it is coming out and going to the diametrically opposite slot and coming out from that slot like this. So this is what I mean when I put dot on one side and cross on the diametrically opposite side. So you can see that still we have the same R phase axis. R phase axis is perpendicular to the two coil sides. So I will quickly erase that and go back to the next one, that is the Y phase axis. So yes, we can realize the Y phase axis also. If I put the Y phase coils here, and in order to have the axis direction, we can put cross here and dot here, right? Now if I go to the B phase, that is we want to realize this axis, then I can fill this entire this slot with B phase coil, and I have to put dot here, cross here. Now you can see that we have the same machine construction, but we can realize it with some other way also. There are other ways of realizing this also other than the concentrated winding. So this is the because the coils are basically distributed. It is not wound around one single pole, but the two coil sides of a coil are actually in different slots, or around two different poles. So that is why it is called distributed. The two sides are distributed throughout, and this is the same realization of a stator, basically rotating magnetic field, using a same geometry, same construction with six slots and six teeth, and we can still have the same thing. And I have shown the what we have just realized in the right hand side picture. So you can see that we can realize R phase vertically, we have realized Y phase 120-degree apart and B phase 120-degree apart. Now just to give you a view, so this left hand side picture is for the consider is a 3D view of a machine stator with concentrated winding. So you can see that the coils, you should be able to see that this is the pole, one coil is basically wound around this pole. So this is wound around this pole, and this is going all the way axially, and again it is coming back like this, right? So this is the case for concentrated coil. But in this other side, in the case for distributed winding, you can see that if this is one coil side, this coil is not going to the exact next portion like this, whatever dotted line I have indicated, but it's instead it's going to some other slot, and like that it is completing its path. You can also see that it is not exactly at diametrically, it is not the diametrically opposite slot. So we can have different we that is not a mandatory thing. We can have different things also, like you may have heard the term like short pitching. We can do some kind of short pitching in the distributed winding. So as of now I am not going into that. So we have visualized the case for distributed winding, or we have understood the distributed winding, how to realize that. So this is the construction, and this is the winding distribution of different coils. And if we excite the same current, that is three phase balanced sinusoidal currents through that, then this is the animation that we are going to look at now, right? You can see that it is rotating. Still we have two poles, and it is a rotating magnetic field. The magnetic field is continuously rotating. So if I just stop and look at different instance, then initially the axis is somewhere here, Now if I move ahead and stop somewhere else, then you can see that the axis has actually rotated in the anti-clockwise direction as now, and now has reached somewhere here. Now if I further go, it you can see that it keeps on moving in time. So if as I move it slowly, I think you are clearly able to see how the magnetic field is actually rotating in space, right? So this is about the rotating magnetic field using distributed winding. Now we will quickly look at the different instance to slowly see what happens. So this is the first instant of omega t equal to 0 degree. So this is how the field is, and actually if we plot the B distribution around the air on different points of this air gap circle with the same convention that radially outward flux lines uh, is given positive B, and radially inward is actually assigned negative sign. So we have this type of distribution, and if I move ahead by 90 degree in time, that is why I reach this omega t equal to 90 degree. It is possible, you can see that it has actually moved, it is actually moved ahead. Earlier it was somewhere the peak was at theta equal to 0. Now it has moved to theta, peak has moved to theta equal to 90 degree. So it is moving at the same rate at which the time is changing. So time is changing by omega t equal to 0 degree to 90 degree. The magnetic field in the air gap is also moving in space. That is space, by space what do you mean? It is actually moving in the air gap, that is a physical space. So it is moving in physical space at the same rate, that is it has also moved by 90 degree. So now let us try to look at the animation and confirm that. So we will see that as the current completes one complete electrical cycle in the space, the field will also move by exactly the same angle. So if I play that, you can see that uh, yeah, the flux, as time is progressing, the flux density distribution in the air gap, that is also moving. Now this is the zero time instant. So is the peak is at theta equal to 0 degree. And if I go back, as I go ahead, it is 90 degrees. So the peak has moved by 90 degree. If I reach omega t equal to 180 degree, it has reached by 180 degree. And again it is moving and um, it reaches 360 degree. That is same as the initial position as we complete one complete electrical cycle. So uh, and also it is to show you that we can actually have, with distributed winding, it is possible for us to increase the number of slots and distribute the winding accordingly. So if I just quickly go back to the earlier case, here we had 6 slots, right? Here we had 6 slots. So we had 3 phase winding, so each phase had 2 slots per phase, because we have three phase three phases. So we have 2 slots per phase, and we are assigning 2 diametrically opposite slots to each phase, and we are maintaining the 120 degree phase shift in the axis, and that is how we are realizing it. Now instead of 6 slots, if we have 12 slots, now we have 12 slots, still we have 3 phases. So what is the number? What is the slots per phase? So 12 by 3 is equal to, we have 4 slots per phase, right? So if we have 4 slots, one slot, so if we have 2 slot, one slot carried dot, another slot carried cross. If we have 4 slots, 2 slots will carry dot, 2 slots will carry cross, and they will be 180 degrees, that is diametrically opposite to each other. So this is how the construction is for the 12 slot case, and we assign one cross, then the diametrically opposite we put the dot, again we put cross, and diametrically opposite we put dot. So in effect you can see that this whole thing acts like a single dot, and this whole thing acts like a single cross, and still we can have the same R phase axis. So similarly, if we have 24 slots instead of 12, then this number increases to 8. So if it increases to 8, then we can have four conductors. Basically, we can have four slots filled with cross conductors, and four other slots corresponding to the same phase filled with dot current. So this is the construction. Here you can see that four slots, side by side slots, they form kind of a band kind of a thing, and you can have these four conductors or these four slots, basically uh, adding the dot that is a net dot that we are having, and we have the same R phase axis as the previous case, and we can actually um, distribute the other phases also in the same manner, and we will briefly look at the impact of that. So this is the comparison of the distribution of radial component of B along the angular position, that is the space, that is the radial or the circumferential position, that is the space angle. And you can see that I have also plotted with blue dotted lines the fundamental component of that, the fundamental sinusoid that we are interested in. So you can see, and the bottom plot basically gives a Fourier series. So this is a periodic waveform. So any periodic signal can be decomposed into the fundamental component and its different harmonics. So here I indicate the fundamental component and its different harmonics and their corresponding amplitudes. So this is the fundamental component, that is 1. This harmonic order fundamental is 1, and as we go ahead in harmonic number, it is that harmonic order that we discuss, and the vertical scale basically indicates the amplitude of them. So you can see that now this left hand side two plots are for the 12 slot case, and the right hand side two plots are for the 24 slots case. Now you can see that actually this dip in between, the dip, whatever dip you see in the flux density distribution, that is because of the presence of slots in between. So we have two poles, that is two iron, and in between we have some slot, which is slot is generally slot means it does not have any ferromagnetic material, so it has higher reluctance. So because of that, the flux density is actually quite low in this region, and we'll have a better look at it when we go ahead. But you can understand why the dip in between is coming. And actually, if we go to the 24 slot case, then you can clearly see that we have many more notches. But overall, if we see that the fundamental component almost remains on the same scale, on the approximately the same value. Let us not focus on the fundamental component. We can obviously, because we are increasing iron part in the slot, so even flux density value fundamental will also go up a little. But focus on the harmonics. We are significantly reducing the harmonics. So earlier we had these harmonic amplitudes quite high, but now we have lower harmonic magnitudes. And yes, so that is what the advantage that we get with going for higher slots. And you can understand that this advantage we can only gain for distributed winding. We cannot have that option for concentrated winding. It is possible to show that if we go ahead and increase the number of slots in the concentrated winding, first it is difficult to wind that way, and then it does not give that much advantage in terms of harmonics in the space, that is B distribution harmonics. It does not give that much benefit out of the by increasing the number of slots. So that is why mostly when it is when we study about AC machines, the as soon as we start, the discussion starts with distributed winding, but it does not mean that the rotating magnetic field can be produced only by distributed winding. It is possible to produce distributed winding by concentrated winding, which is very similar to the stator field winding in a DC machine. So that is why I have started from the DC machine field and started slowly modified it to realize the rotating magnetic field. So this is the animation of the 24 slot case. 24 slot, it still has two poles only. So you can look at that we have one single magnetic axis. That means one side it is north, another side it is cross. Now if I run the animation, we'll be able to see that it is rotating. You can also see the smoothness in rotation. Earlier, because of so many number of slots or significant uh, width of slots, there was some kind of disruption in the magnetic field distribution also. But but here you can see that it is very quite smooth. The rotation, it still runs at the same speed. If I don't know whether it's visible to you, here you can look at the time. It is in milliseconds. So total duration is for 60 millisecond. And if I restart it again, so initially is 0 millisecond, right? And as we go to 20 millisecond, you will see that it has come back. It has again come back to the original position. It started rotating, then it became opposite like this, direction in the opposite direction. It came to this 270 degree, and after 20 millisecond it again came back to the original position of the magnetic field. So this is a simulation for a 24 slot two pole machine, because there are only two poles in this case. Now can we have four poles instead of two? Is it possible for us to have four poles, and how to do that? We'll briefly look at that. So this is the construction for a four pole machine, where you can see that we have 24 slots. We have 24 slots, and number of phases is three phases, right? So the slots per phase is basically 24 by 3, that is 8. So we are putting so four slots we are filling with cross conductors, and four slots we are filling with dot conductors. That is what we are doing for realizing two poles. Now the important quantity in this case, uh, which did not matter because we are discussing about two pole machine. Now in order to go for four pole machine, we need to actually calculate slots per pole per phase. So what is the number of slots per pole per phase? So if we go for two pole machine, it is basically 24 divided by 2 into 3, that is 4, right? So we have a band, we have a uh, belt of four side by side slots, which are filled by the same direction, same polarity of current, that is cross in this case. And again the opposite belt of the same phase is actually filled by cross dot conductors. So this quantity 4 is important. 4 basically gives you slots per pole per phase. So if this number is 4, then we have to create a belt of 4 slots and fill the slots with the same polarity current. Now if we actually calculate the same thing slots per pole per phase for a 4 pole machine having the same number of slots, that is 24, 4 pole, that is 4, and we still have 3 phases, so the number that we have is 2. So in this case, as I move to the next case of a 4 pole machine, probably I'll need to remove all those things for clear visibility of this case. So the important thing I'll note down. So slot per pole per phase, this is nothing but slots per pole per phase, right? So this is basically, this is slots per pole per phase. So this is the thing. So slot per pole per phase for this case, that is if p equal to 2, then we had this slot per pole per phase number to be 4. But if p equal to 4, then we have this slot per pole per phase number to be 2. So in this case, because we had slot per pole per phase SPP number to be 4, we had constructed a belt, a phase belt of 4 consecutive slots, which we filled with the same polarity of current. Now, because we have 2, so you can see that we are filling dot conductor at a time by only 2 slots, right? Then we are what is the sequence in which we fill? So first we fill red cross, then we go to B dot, blue dot, then we go to yellow again cross, then we reach red again, we put the red dots, then we go to blue again and we put blue cross, then we finish with yellow dot. So we have these many belts. So this is another belt, this is the last belt, this was the third belt, this is the second belt, and this is the fifth belt, and this is the third belt, fourth belt to be specific. So the sequence in which we go is first we fill 4 slots, which is nothing but the slot per pole per phase number. We fill 4 slots with red cross. Then we move ahead and fill again the same number, that is 4 slots with B dot conductors. Then we move ahead and fill 4 slots by yellow cross conductors. Then the sequence continues, and such we have six belts in total. Now if I have to follow the same sequence for this case, follow the same process for this case of SPP equal to 2, first I have to fill in 2 slots with red cross. So this is the first case. Next I have to move to blue dot, right? So next blue dot I fill in 2 slots. Next my sequence tells me yellow cross. I fill in 2 yellow cross. Next my sequence brings me to red dot. So I fill 2 red dots. Next my sequence tells me to blue cross. Yes. Next I move to yellow dot. So I fill in some yellow dot also. And my sequence for the two pole case is now over. Now because in the same sequence, so again I'll start from red cross 2, then we'll have blue dot 2, we'll have yellow cross again 2, we'll have again red dot 2, blue cross 2, and finally yellow dot 2. Now you can see you have how many phase belts. You have 12 phase belts, and each phase belt is consist of two slots. So for this case we have uh, this combination of two slots, and we have such a combination of two slots comprising one phase belt, and that is basically um, having how many 12 phase belts in total. So let us see if we excite it with the same thing, if we excite it with the same sinusoidal excitation. So first thing, what we can see, what we can clearly see is it is having four poles. That is very clear to us. So first we'll look at the thing in the okay, we are going to look at it in, yeah, we are going to look at it at different locations what happened. So I'll simply run the animation. Yeah, so you can see that we have four poles, and that is actually rotating, that is rotating, and we have created a rotating magnetic field with four poles, with appropriate modifications made in the winding distribution. With the same number of slots, we are just redistributing our winding a bit, or winding distribution we are changing a bit, and we can have four poles. And how to visualize it? So if I draw one flux line for each case, each pole pair. So this is one kind of flux line, this is another kind of flux line, this is another kind of flux line, and this is another kind of flux line. If I now indicate some directions, if this is every flux line is close to a line, so if I assign some arrow sign like this, it has to continue like this. We'll find that this also has the same arrow, and it is coming out like this, so forming this whole thing. This whole thing is like a south pole that is getting formed because flux lines are entering the stator. So this is one south pole. Now here flux lines are coming out, here also we will find that flux lines will be coming out. So this portion creates another pole, that is north pole in stator, right? Now because it is going in, we will find out that this also goes in and comes out like that, right? So this whole thing forms another south pole in stator, and again if this comes out, then this already we have seen that it also comes out from here. So here we have another pole, that is the north pole, another north pole. So overall you can see that we have four pole formation, we have two south poles and we have two north poles. Now I'll erase all of these and show you the speed of rotation. So now if I now this is 0 second as shown here. Probably it is not very visible here, but I'll move ahead in time by 20 millisecond. Okay, let us mark that, let us go slowly. So we have this magnetic field here. So as I start moving, you can see that it is also moving. Now I'll stop at when it reaches 90 degree. When it moves by 90 degree, what is the time? If I look at it, I'll just write down it for you. This is 10 millisecond. So we have completed half electrical cycle, and in space it has only moved by 90 degree, that is quarter of a full cycle. Now I'll further move ahead in time. So you can see that it is rotating, and now it has completed 180 degree of rotation. It has reached here, and the corresponding time is actually 20 millisecond, right? So 20 millisecond means for 50 hertz current excitation, one electrical cycle is completed. in 20 millisecond, but the field, magnetic field in space, that has moved by only 180 degrees. So the electrical omega t has moved from 0 degree to 360 degree, but the magnetic field theta, from theta equal to 0 degree to, it has only moved by 180 degree. That is where the difference comes for electrical and mechanical angles for higher number of pole cases. So so we can see that it is simply divided by two. So the mechanical angle, so theta mechanical is half of theta electrical, right? This is the theta electrical, that is omega t, and this is the theta mechanical, which is the spatial angle theta. So you can see that when omega t or theta e completes 360 degree, theta m only has moved by 180 degree. So this gives us this relationship that theta m is half of theta electrical, or theta electrical is twice that of theta mechanical, and 2 is nothing but the number of poles here, or number of pole pairs here. So number of pole pair is p by 2 theta m. So this gives you that well known relationship between electrical and mechanical angles for an AC machine, or yeah, for a machine. So you understand, or you can visualize where it comes from. So now we'll stop at different locations and look at the the B distribution. So this is the first case of a two pole machine. You can clearly visualize that we have a portion, so so from 0 to 190 degree we have all positive flux density, then again this 270 degree to 360 degree we have positive only. So this is like one pole, right, and this is like the other pole where it is negative. So there are two poles in this case, and we are at the 0 degree location. I'll run the animation to show you how it rotates. So you can see here that after omega t moves by 360 degree, it has moved by, so we are again back in the same location where it started from. Now if I go to the four pole machine, here again we are starting from omega t equal to 0. So so this is like from 0 degree to here approximately 45 degree we have positive flux density, then this portion to here we have again positive flux density. From 45 degree to 135 degree we have negative flux density, right? We have negative flux density here. Now for 135 to 225 we have again another positive flux density, and again 225 to 270 we again have negative flux density. So we have four portions. So from this portion to this portion this is a negative, from this to this there is a negative, a positive, again a negative, again a positive. So we have four poles in this case, and if I move it, if I run the animation, then you will be able to see, yeah, could you see that it has only moved by 180 degree? The same thing which started from here, that has only moved in space by 180 degree, when theta omega t has moved from 0 degree to 360 degree. So this also tells you about electrical and mechanical angles, which become eventually different for a four pole machine, but in case of two poles it remains the same. So here I'll stop a bit for in case anyone has any question, then we'll move to the next portion.
Samrat, one
Yes.
question.
Yes.
Why should we go for higher poles? You mentioned what is the point of going for higher slots, that it reduces
Yes.
the THD. But
Yes.
why should we go for higher poles?
Actually, if we go to higher poles, then we can reduce the speed and we can increase the torque. So if we actually within the same so within the same so considering a machine dimension is fixed, so the power it can deliver is fixed. So if we reduce the speed, then we can take more torque out of the same machine. So if we have
Mhm.
lower speed requirement, then we can actually go for higher pole machines.
And how is it reducing the speed?
uh, reducing the mechanical speed, because the
Okay.
mechanical angle uh, if I
Is
say
only half of the number. Yeah, it's
yes,
getting
yes.
reduced with the increasing number of
So the
poles.
mechanical speed is very close or exactly equal depending on whether it is synchronous or asynchronous machine. It is becoming half for four pole machine compared to a two pole machine.
Okay, so we can go for higher torque in this case.
Yes.
Okay, understood. Thank you.
Any
Sir,
other question do you have? Yeah.
sir, in slide number 21,
Hmm. Yes.
21. So, so here for our phase, we are
Hmm.
actually, if a total number of turns, let's say n, you are dividing it by 2, and you are creating two such poles. For example, R phase, you have a top and
Yes.
bottom you have utilized. Rather than that,
Yes.
you can just divide the entire machine into three parts, and you can just use that part. Why we have to separate it out?
Come again, I did not get you.
So in the concentrated case, we have a
Huh.
pole portion and bottom pole portion.
Correct.
We are using it for the R phase. Rather than that,
Yes.
you just divide the entire machine by three, and wow, and use one particular portion for the R phase, other portion for Y, and other portion for B. And why we have to separate into two parts?
So what is your proposal? Can we? So your proposition is, can we make uh, so say all poles like this? So red pole is only like this. So this makes this kind of makes up the red phase. Then yellow, because we need to have 120-degree phase one. Okay, it was vertical, so I'll maintain it vertical to avoid any confusion. So probably I'll do it on the same structure. So we are only using this dot, we are using this cross, right? Next we will uh, next we are going to yellow phase. So we will use this whole cross, right? We'll use this whole cross, and we can use this whole dot. We can we can use this whole dot, red dot, and we can use this whole red cross. And then blue, we'll have it the entire thing as blue dot, and we'll have the entire thing as blue cross. Is it what you are referring to?
Yes, yes.
Yeah, so yeah, it will also create the same rotating magnetic field. There is no issue in that. uh, what will be the, so let us try to see what happens instant by instant. So earlier case we were very sure about the flux flow, the return paths. So let us try to see what happens here. Have to see. So if it is dot and cross here, then flux lines will go in, right? Flux lines will go in here. Now if it is for this YOLO phase, if it is cross here, and say we are at say omega t equal to 90 degree, so Im is IR is Im. I should basically use smaller letter for that. Iy is minus Im by 2, and Ib is minus Im by 2, right? So whatever is the flux at this instant, it will be twice. To basically, I'll indicate by 4 flux lines here. So if I indicate it by 4 flux lines in this direction, that is, if r is positive, that is, this remains dot and this remains cross. But because Iy and Ib are negative, so whatever polarity we have indicated for positive current, that has to flip. So instead of cross here, we would have dot here, dot current here, because the current magnitude itself is negative, and it will have cross here, right? So if it is dot and cross, then flux lines have to come out from there. And if it has to come out, then because the amplitude, because the current is actually half the current of R phase, so if I have indicated with 4 flux lines here, I can only indicate with 2 flux lines here. Similarly, if I go to the blue phase one, then here it is dot, that means it will become cross, and this is cross, so this will become dot. So the black dot and cross are the dot and cross for the time instant. So if it is cross and dot like that, then it will be also coming out, and because the current is half, the flux line should be like this. Now how will it flow? It will basically flow to here, flow to here, like this. It will complete its path, and similarly it will flow here and flow here, like this. It will complete its path, right? This is how your field would look like at this instant. And if you actually plot the B distribution, you can find that you have a bigger zero region. So this whole region that I am so this whole region which I am pointing to, this whole region will have zero flux density. Similarly, in this whole region we'll have zero flux density. Probably I should use some other color. So this whole region will have zero flux density, this whole region will have zero flux density, and this whole region will have zero flux density. We would have more concentration in the flux density distribution, and it will be more further away from sinusoid. So earlier, now also with concentrated winding, you can see, if I go back to the case, it is quite far from being a sinusoid, right? It is quite far from being a sinusoid. But if I use this type of distribution, it will also rotate. Whatever you can see here, so the field direction is like this, overall field, and it is return is through here. So it will also have a rotating field, but the B distribution will be more further away from being a sinusoid. It will not be a sinusoidal flux density distribution, right? Does that answer your question?
Okay, okay, sir. Sir, can you please comment on the harmonic order? We will get even or odd number then?
Always it is. Now I see that it is becoming. For this case, the it may not have half-wave symmetry. If it is not half-wave symmetry, then it will have even harmonics as well as odd harmonics. But in this case, at least, you can look at the waveform and comment, clearly see that there is a half-wave symmetry in this case. So if there is half-wave symmetry, then that means we can only have odd harmonics. We cannot have even harmonics. So yeah, for this type of distribution, yeah, thanks for pointing that out. For I feel, if I plot this, distribution, then we may eventually have even harmonics also along with odd harmonics, but uh, it harmonic magnitudes will also increase. But this odd and even
But
half wave symmetry case I have to plot and see. But yeah, no doubt that harmonic magnitude will no doubt will, without any doubt, it will increase.
Is it
hello,
good to have
Samraj.
a odd harmonic or a even harmonic?
Yeah, come again for this case.
No, generally, is it good to have a
Generally, yeah, generally if we have a, yeah, generally this for this type of distribution either this I should probably go to the harmonic content. I have a picture for that. Yeah, this is the general case, so you can see that you can look at the harmonic orders. So where do we have some non-zero values? This is at 5, this is at 7, this is at 11, this is at 13. Basically this 17 and 19 is very small, this is not even visible properly. Then again we have this 23 and 24, 23 and 25. So we have generally we have 6n plus minus 1 harmonics. We do not have triplen harmonics, third harmonics we do not have. And yeah, we have this, generally we have this 6n plus minus 1, these harmonics where n goes from 0 1 2 like this. 0 it is only fundamental, there is no negative. So yeah, negative 1 harmonic. So yeah, so we have 1 5 7 11 13. These are the, generally we have odd harmonics only because we have half wave symmetry in our B distribution waveforms.
so why we have to have a B needs to be a sinusoidal one? Any advantages we will get
If we
when we are
want our
making?
induced EMF, if we want our induced EMF to be sinusoidal, which is very close to, so our induced EMF is basically nothing but the flux linkage, rate of change of flux linkage. So if we want that to be sinusoid, then we need our B distribution to be sinusoid also.
Okay, okay.
We will look at that once we reach to rotor and understand what is what is the what is flux linkage from B distribution. Then we'll see that, yeah, if it is closer to sinusoid, then we would have our induced EMF to be sinusoid also. And what is the advantage of having induced EMF sinusoid? Then we can have, so if I try to plot, if I try to draw uh, equivalent circuit. So say this is the terminal, these are the two terminals. Now each any winding will have some in resistance. It will also have certain leakage inductance. Now there will be some induced EMF. Now this induced EMF into current. This is what the electromagnetic energy conversion, that is getting converted to magnetic energy. Now EA into IA, if we have this this as sinusoid and this as sinusoid, and if we have similar tree winding, and if the then the total electromagnetic power will be EA into IA plus EB into IB plus EC into IC. And if we have all these things to be sinusoidal, EA, IA, EB, IB, EC, IC, and if you do this math, and you will find out that this power, instantaneous power will be a DC quantity. So this power, this is instantaneous power, that is small p. This is always a capital P, that is it is having a DC value only and it has no pulsations. So that means our torque is nothing but power divided by omega, and the speed, the variation in speed in electrical terms, that is quite low. Please mute yourselves unless asking a question. So the variation in speed is very low. So because we do not have any harmonics in power, or we have a DC power, instantaneous DC power, it does not a constant instantaneous DC power input or power converted to magnetic energy. So that means this equation tells us that we have no torque pulsations also. So basically in electrical machines we can have zero torque pulsation. We can have a steady DC torque without any ripple on that, ideally. So that is the advantage of injecting sinusoids, because theoretically it is possible to have constant power in time, and it is possible to have torque DC value without any ripple.
Hello, Samratji. Can you please go to 19th slide?
19th.
Uh, Now what?
Okay.
What? No, no. Like 21st. Sorry.
21st.
Uh,
uh,
yeah. Here now whatever you discussed earlier. So like if I can see towards our face, right side is a cross and left side is a dot. Okay.
so
Suppose if I
are you
swap that.
discussing 1 minute?
Uh,
So are you discussing anything regarding the question asked, that is if we, what happens if we, instead of two poles, instead of distributing the R phase coils, can we so are you asking anything regarding that, or regarding what I discussed
Yeah,
initially?
yeah, here only. Yes, yes, regarding this one only. So
Okay.
now our face you have marked with that pink indication arrow is there, right? So
Yes.
here now left side you indicated as like that is a cross and left side it is a dot. Now if I
Hmm.
swap that, my
Hmm.
flux direction will change it towards
Yes.
downside, correct?
Yes. Yes.
So
Then accordingly we have to change the R Y phase and B
okay.
phase
Now in that
polarities
case,
also, right? No, no.
no,
If
let
I
it be that
change,
same. Let it be.
no, 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 we cannot have the same, because we need to have R phase axis, Y phase axis, and B phase axis 120-degree phase shifted. That is the basic need. We have to have that.
Okay.
We cannot have, we
Okay.
can then we will not have a rotating magnetic field. So in this case also, hypothetical case we can always discuss, but that will not produce a rotating magnetic field. For rotating magnetic field, yeah, as the question was asked, we can, instead of two poles for R phase, we can have one pole only, and for one pole we can have our Y phase, and one pole we can have B phase. That is true, but we have to have, so in this case also we are having rotating magnetic field. Only the case being we have more harmonics, and that is away from sinusoid. Yeah.
So
So
now
if
if you can
we
see,
uh,
if you can see here towards our face, my your indications where a dot and cross you have kept. So
yes, this
if
is
I
dot,
can
right?
see, that is dot and this is cross. So if you say
Yes.
this segment, one belt, one this pole, like together that black circle, whatever you have made, that is a pole, right?
Yes. So
And
this
this
is a
is also
slot, wherever this is the slot, but what I have made, yeah.
that is a
This is
slot.
one pole. Yeah, that is a
That is
pole.
that is
That is the south pole. Yes.
South Pole. So now in this scenario, it is two pole. This is a two pole only, right?
This is a two pole only. This whole thing acts like a combined uh, north pole. Although it has in between it has zero, but no flux lines will either come out or leave from there. So this whole thing will act like a north pole. So still it is two pole machine only.
So now the type of winding is what winding it is? It is a concentrated. We can call it as a distributed in this now.
It is concentrated only because as I discussed earlier, where was that? Concentrated means the two coil sides are around the same pole. So if we have a pole, then the two coil sides, that is this coil side and this coil side, they are around one single pole, one single tooth, to be more specific, because pole can be confusion. So if that is around a single teeth or tooth, then it is concentrated. But
Now, if I
when
if I
when
can
is
see,
it distributed? if the two
So
coil sides are not across the same teeth. Now you see, this is a coil, this is a distributed coil.
yes,
This
yes.
coil
Distributed
side,
is clear. Distributed is
yeah,
clear, but to concentrated only. So here now, if I can see as a cylindrical one cylindrical surface. So
yeah,
like if, in a cylindrical surface, right side and R side, if I can assume. So R side it goes as a cross, and one path like completely it will go, and then it will come towards the R side, and it will comes out, right?
yes,
Right side it will enters as a cross, and then left side it comes as a dot, correct?
yes, that is true. Here,
Yeah,
if the current direction is like this, then here it goes as cross in
yeah,
this side.
yes.
Probably I'll use some other color. So here it goes as a cross, and here it comes as a dot. So this is what we represented here, right?
Yes.
Now the ink can be removed from here because I saved it. But if I go back to some other case, this is, if this is cross, this should be dot. So in side view, if we look at the same thing from this view, and
Yes.
this surface, then it will look the same.
Now it will not end, right? Normally, the whatever the conductor it is there now, where it comes as a dot, then again it has to link with the again it has to pass through the same cylinder, right? So again, how it enters?
So the different turns, are you talking about different turns?
No, no. Now, if I can see RYB three phases
Yeah,
in any like so three phase. So R phase comes as like a number of turns will be there, so many terms and number
okay,
of so many
okay.
slots will be there. So one side
Ah,
it will be enters, and then one
ah,
side finally it comes out. So that is one
yes,
phase. So
yes.
now in this case, whatever we are seeing here, so that is one
Ah.
phase. Shall I call it?
No, 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 this is not one phase.
Uh,
So this is one coil of our phase. It
okay,
comes out, say whatever
okay,
way it comes out,
okay,
and these are the two terminals. Here it goes in, here it comes out. Now
correct.
you have the diametrically opposite one also, right? You have the diametrically opposite pole also, or a tooth also, where you need to wind. So if it is dot and cross, this side has to be dot and this side has to be cross. So wherever it is coming out, that has to, we have to take and actually take it like this. Like this we will wind, right? We'll wind it
Okay.
like this. Again it will come back, and this will form our two terminals of the phase.
Okay. So this is one phase, R phase now.
Yes,
Okay. Similarly, Y and B phases is also same.
yes,
And one more thing now, like
yeah.
so in general industrial applications now, most of the cases handling with the distributed winding only now, if I can see, because less harmonics comparatively with my concentrated.
Yeah, most of the, if you if yeah, most of the cases, unless very special cases
Mm-hmm.
where very high torque is required and
Mm-hmm.
speed requirement is low, all the
Okay.
cases will have distributed winding only. So only cases where it is very high number of poles, say uh, very high number of poles, 48 poles,
Yeah,
36
that time speed
poles,
is very less, right? If whole number, if it is
that
increases,
is,
speed will
speed will be very low, and
very
we
low.
will, yeah, speed will be very low, and we only distributed winding or concentrated winding will be good enough for us.
Yeah. So, and one more thing. Now, in DC machines, specifically, we do not have any frequency component. So, we have to talk about harmonics.
No need.
No need, right? Normally, whenever frequency terms it comes into the picture, then only we have to discuss about harmonics. Correct?
Yes.
Okay. Thank you.
DC machine, we would go instant by instant to understand what happens, what is the flux linkage of coils. Basically, we'll understand now from till now whatever we have discussed. If I summarize,
Okay.
we have discussed how to produce stationary magnetic field. That is,
Correct.
we can have concentrated winding, and we can inject a DC through it, and we can have a stationary magnetic field produced. Now next problem was can we produce a rotating magnetic field? The stator will not rotate, but the magnetic field will rotate. So the windings will not rotate, but the field produced by the by the windings will rotate. So we have realized how to produce that magnetic field from basics. That is because concentrated winding was most clear to us. So we started from that, and we realized that okay, so there can be something called distributed winding, and we can produce the same thing there. And we have looked at the advantages of using distributed winding, that is we can reduce the harmonics in B distribution, which is generally talked as space harmonics. So we can reduce that, and we can after that, because there is an interest of changing number of poles, so is there a possibility to change the number of poles that we can produce and still a rotating magnetic field? So we have discussed that. So the next day we will go into the rotor magnetic field, and that will bring the differences between the two between different machines. So next day we will start with uh, so the realization of the stator magnetic field is over. Now the critical portion that will clearly discriminate between the three types of traditional machines that we have: DC machine, synchronous machine, and asynchronous machine or induction machine. How we realize the rotor magnetic field will mark the differences between them.
So in all cases, with respect to the stator side, like the field like whatever the field injection, whether it is in AC or DC, we have discussed so far.
Yeah,
So
yeah.
now with
One case
respect to
is DC,
with
another
respect,
two cases are AC.
yes, correct. So now which type of machine if we want to discriminate in this, if we want to discriminate means now the realization of rotor field is necessary. So here
Yes.
it comes like now whether which motor it, and we can categorize that. Correct?
First we'll see what are the, so which motor will come later, because we are starting
Yeah,
from
yeah.
fundamentals. We do not have,
Mhm.
we have different motors in our mind because we have studied it some way or the other. Not sure how much understanding was there, but yeah, we tried to, we are trying to approach the problem from basics. Okay, how
Okay.
can we realize that, or what is the basic thing that we need, and we can realize it. Now we just the way we realize that okay, we can have rotating magnetic field with two types of winding, and maybe any more number of winding is also possible. We don't know if we look into that. But similarly, can we have, so if I summarize the initial discussion, the first day discussion on the realization of rotor magnetic field. So our rotor is rotating. Rotor is rotating, right? That means the conductors which are sitting on the rotor, they are also rotating. Now the problem is, can we have, for the first case, can we have the stationary rotor magnetic field? Although the rotor is rotating, but can we have stationary rotor magnetic field? Second problem, can we have rotating rotor magnetic field? And we will see that we can have that in two ways.
This is where this is where that our statically induced EMF and dynamically induced EMF will comes to the picture, right?
Uh, no, stationary both all cases it is induced EMF is
EMF will
DC
induce
dt.
EMF.
Yeah.
Yeah, EMF will induce. But the thing is now again that like about if I discuss about some stationary magnetic field, again it will go to the transformer topic.
Yeah.
So now with respect to the motors only, we have to discuss dynamically induced EMF only, correct?
Yes. So the stationary magnetic statically induced induction of magnet or induced EMF, that is only for the case of transformer. That is
Yes, yes, correct, correct. Yes.
not there in machines. Yeah.
Yes, yes, yes. So, with respect to the rotating machines, like we have to talk always about dynamically induced EMF only.
Yes. Yes. Always decidity, where because decidity is most common. Now we can have which is changing, whether theta is changing or not. Yeah, that is the discussion. Yeah, here the because we are talking about rotor is moving, so the rotor windings are also moving, so always dynamically induced EMF.
Sir, when you increase the number of folds, what will happen to the magnitude of the air gap flux density? And can you comment on the copper usage in both the cases for the pole number equal to 2 and increasing the pole number?
That is beyond the scope as of now. Those are possible to be seen. That will be a more detailed design course. Yeah. So copper usage, the the comparison of flux density distribution. Yeah. Basically, if for this comparison, I do not have the 2 pole and 4 pole using the same copper. What is the B magnitude difference that I do not have in these slides? Yeah, that is somewhat beyond the scope of this lecture that we are having. But yeah, you can find it in regular uh, books, design related books.
Excuse me, sir.
Yes.
So the in this today's class, so how the poles will be going to decide, based on the magnetic field, na, sir?
How the poles is
Is
going to be
yeah,
poles means
in any
north pole,
machine.
south pole, like that, or
No, no,
what is the number of pole
like
you
a
want?
number of poles.
Number of poles will be based decided on what is the speed you want. If it is an AC machine, so if your
Okay,
speed is say 3000 rpm, you have to go to, if you have 50 hertz supply only, then you have
okay.
no choice other than going for 2 pole machine. If you have around 1400 1500 rpm, then you can go for 4 pole machine. It is dependent on the machine speed that you want.
So right now, which you showing in the slide, in this slide, what is the how many poles it is having? Four pole, na?
Yeah, it is having 4 pole, as you can see from the magnetic field also. Here it
Okay,
is
that's what
a
I am
pole.
telling. Like through
Yeah,
the magnetic field, we can decide, na, like how many
yeah, yeah,
poles also.
yeah,
Mm.
yeah. Seeing the magnetic field, we can tell clearly that what is the magnetic field here, what is the number of poles here. In the two
Mhm.
pole case, if I go, it is like this. Can you see that there is one single magnetic
Only
axis?
single is there. Yeah.
But if I go
So
to the next
normally in
case,
general cases, how we will be in like practical cases, how we will be deciding? So speed
so
based on
so the
speed.
problem so the problem is you have a machine, you don't know the winding configuration, and obviously you
Yeah.
cannot see the field. How can you
Yes.
know the number of poles, right?
Yeah. Yeah.
Yeah, if it is an AC machine, then you
Yeah.
have to look at the nameplate. If it is 50 hertz and if the speed is around
Three
close to
thousand.
1500 rpm,
1500.
then
Yeah.
it is 1500 rpm, then it is 4
Okay.
pole. And if it
Okay.
is exactly 1500, then you know that it is a synchronous machine. If it is
Mm.
around say 1475 1450, like that, some
Mm.
speed close to 1500 but not exactly equal to 1500, you know that it is an induction machine.
Okay.
It is
Mhm.
around 1000 means it is a 6 pole machine, like that. You have to
Okay. Okay.
look at the excitation frequency and the speed.
Okay. Yeah. Thank you, sir.
Yeah.
Hi, Samrat.
Just a minute. Now, from the just a minute.
Yes.
Now, from my winding configuration. Now, how I'll be identifying that this is a four pole and that is a two pole. Now, can you please just whether I missed that point or like from the winding point of view?
Okay, so from winding point of view, so in case your coils are colored like this, so most machines they will color, they will put colored insulation tapes on the machine windings, basically at least the end windings. By end winding I mean
Okay.
this thing, where is that, this 4 poles 2 pole. Yeah, basically this end winding portion will be colored mostly. Okay, if you have the machine open, in some cases they may not, but yeah, but still you can look at the number of belts phase belts. So if I go to the specific case, yes, can you see that here, if you look at the end winding, how will it look like? It will look like that four things are going together, right? It will go look something like this if you look at this case. But if you look at this case, it will only like two are going, and then you have to count how many of them are there. Like in this case, for R phase, you will have basically you will have only where is that? Did it close for you?
Yeah, we are
Yeah,
unable
it's
to
not
see that
visible.
screen.
Okay, I'll bring that back. Presenting and again come back. Yeah, is my screen visible now?
Yeah.
Why is it looking like this? I write down. Unfortunately, I'm not able to write down. Probably the battery in the pen is over. So yeah, but we can look at the number of belts that we have in a machine. If we have If we can will be clearly able to understand that how many so here you can see that number of phase belts for R phase is 4. And also you can look at, if you can clearly understand clearly see one coil, then you can look at what approximately what angular difference the two coils are going. If it is if it is almost like 180 degree, if one side is going at some angle and another side is going at approximately 180-degree angle, then you know that it is a two pole machine, as you can say as you can see in the left hand side. But if you see that it is approximately at 90 degree, then you know that it's likely a four pole machine. If it is less than 90 degree also, then yeah,
Hmm.
depending on the angle, it will be either six pole uh, or eight pole machine. Yeah, if you look at one, if you can trace one coil, if you have the machine open, if you can trace one coil, seeing that you will be able to understand.
Yeah.
Samrat, one question. Can you please get back to slide number 21?
Slide number 21. Yeah.
Yeah, in this same slide on the left side, yeah, in this machine, left side machine.
Huh.
So how do you comment about the load carrying capability? Because I am thinking like it will not work even under no load. I'm thinking like that.
Which one? The hypothetical one or the
Hypothetical, yeah, hypothetical. No,
it
hypothetical
will
one.
work. It will work. No
Okay.
load also it will work.
Uh-huh. Because the flux density uh, over a long time seems to be zero.
It will work
Okay, okay.
because the flux
But
density will keep on rotating, keep on changing its sign. So suppose hypothetically you put some conductor. So basically that will be obvious, or clear why that induced EMF is coming in rotor. But if you say put some rotor bars like that, similar to an induction machine, there will be some induced EMF because there is some flux linkage, change in rate of flux linkage, so there will be some induced EMF. They may be or may not be sinusoid. There
okay,
may be
okay.
more ripple, there may be some more noise, but it will work, it will run at least.
Okay. The cogging will be more.
Cogging, torque ripple may be more.
Yeah, yeah.
Cogging is when the number of stator teeth and rotor teeth, they're exactly equal and they do not start at all. That is what we mean as cogging.
Okay, okay.
So
So
yeah, it will
I
work.
mean the torque ripple.
Even torque ripple will be high, but it will rotate.
Okay,
Even
okay.
even we have here we have one setup for only demonstration purposes. There is something called open day. So the entire IS is open for one day where general public can come and see different things. So for the demonstration we had
When
made uh, one induction machine without any core at all, so in the winding distributed like this, and there are some bars where everything is open. It's like a skeleton without any muscle or any flesh like that, still it rotates.
when is
So
that day? Smritji, when is that day? This year?
it is generally February, March, like that.
Okay, I hope we'll
I'll
meet
once
during that time.
yeah, one, if the this thing is the announcement is done, then I'll post it in that group.
Yeah.
Okay. So shall we stop as of now?